All right. The free response just dropped for this year's mechanics test. So it's time to answer the age old question. Chat, are we cooked? Let's see. So, question one looks relatively normal in the grand scheme of things. So, we've gotten some strange looking figures in recent years with weird angles and gliders and all that. This honestly looks like something that could have been on the test 20 years ago. Let's see what they actually did with the figure, though. Let's see. So, I can already tell this is in the scheme of problems that I call conservation. So, I can tell there's a spring here, there's friction here, there's a block here. So, what's happening is a block compressed a spring. So, it's supposed to be out here, it's compressed. It's going to launch the block forward, it's going to slow down due to friction a bit, and then it's going to collide with a bigger block, and we got some ballistic pendulum deal thing happening over here. So it looks like we got energy, work, momentum, energy. I don't know how far they're going to make us go, but here we are. So first, it tells us that at t equals t1, block A is at x equals x1 after traveling a distance xc, moves with a speed v, and the spring is at equilibrium. So here, all of your spring potential energy has been turned into kinetic energy. So no friction yet, just that. So pretty straightforward. Kinetic energy at 0.0 plus potential energy at 0.0 is equal to kinetic energy at 0.1 plus potential at 0.1. Well, block starts at rest. That's 0. But it definitely has spring potential energy, 1/2 times k times compression squared. And at the end, it's definitely moving. It has velocity v. But the spring is now at equilibrium. And at equilibrium, there's no spring potential. So just doing a quick rearrangement here, you can cancel the 1/2. Well, we get 1/2 kxc squared equals 1/2 mv squared. Very typical calculation. Cancel out the 1/2s. We get v is equal to square root of kxc squared divided by m. I know I could pull out an xc from the square root. I really don't care. Derive an expression for the speed v a comma b of the two block system immediately after the collision. Well, I see two block system and I see collision. So we know that obviously it's going to be some sort of a momentum thing eventually. If two blocks are colliding like this and there's no like obvious like angular momentum thing happening, there would be if this was a rod, but so we need to figure out basically what speed is this block coming in with before it hits and sticks together in a perfectly inelastic collision. Well, that's why this part is here. So we can't just use our speed from the previous part because the friction path right here is going to slow it down a bit. So first, we got to get V2. So how we do that is we know that it's going to go over this path D with friction coefficient mu. So that's going to steal energy via work energy theorem. So we know that the work done on the block on that path is going to be its delta K. And what's the work done due to friction? Well, it's always negative. Just going to be equal to negative friction force times its displacement. And, well, the friction force is always just going to be mu times normal because it's kinetic friction. And we're on a flat horizontal surface, so the normal force is just given by our typical nice and clean mg. And now we know what delta k is explicitly. It's just going to be starting k minus, or sorry, ending k minus starting k. So we can just set 1/2 mv2 squared minus 1/2 mv squared, where v is that v from earlier, is equal to work done by friction, negative mu times mgd. And we can do a quick cancel here. Note, there's also a kinematics approach. So when we see our final answer, you might say, oh, that looks like kinematics. Yeah, it is. Kinematics might actually be easier. But regardless, we will see that we can find that from this, v2 squared is going to be equal to v squared minus mu gd. Or sorry, minus 2 mu gd. So now you can totally see where the kinematics could come in, because the acceleration would be minus mu g, so this is just the vf squared equation. But you'd get v2 is equal to square root of v squared minus 2 mu gd. And I know we know what v is, so we'll have to substitute later on. But now for momentum. So we have, you have mass m, and you are going into the collision with velocity v2, and you're going to hit something of mass 3m with velocity 0. And after the collision, you just become a big ol' crate with the desired velocity. So this is perfectly inelastic. So we got two objects converging to become one. So we can just set the initial and final momentum of the system equal to one another. And then by initial and final, I mean right before and right after the collision. So we have a little m moving at velocity v2, which we found. And then after the collision, well, maybe more explicitly, plus the other thing moving at 0. And then after the collision, we have an m sticking to a 3m at the final velocity we're trying to find. So we can see that the velocity after the collision is just going to be equal to 1/4 of the incoming velocity. Which should make sense, because if your mass is going up by a factor of 4, the velocity goes down by a factor of 4. So velocity after the collision is just going to be equal to 1/4 times that whole expression we found earlier. And I'm just going to write what that v squared is, because technically v is not an allowed variable, because we were not given it originally. I'm not sure you would be penalized for not back substituting this, because if you define v up here, but just for completeness, we'll do that. Minus 2 mu gd. Lovely. Yeah, very classic. So this is very classic style College Board up here. And now we have this lovely graph from hell of getting the kinetic energy over time. So they pulled something like this last year, I remember, with some sort of a spring on E&M of all places. But we have to graph the kinetic energy as a function of time of block A as it goes from the start to T3. So K versus T, well, we have to realize that the functional dependence is going to matter here. We can't just draw points and connect them. It's going to matter how we do it. So instead of thinking about this as K, I like to think of this as V squared. Because 1/2 m is not changing throughout this whole process. So I'm just thinking, how does V squared change? So that will involve, obviously, figuring out how V changes. So let's start. The best way to do these graphs is to get the points correct and then think about connecting them. So at time equals 0, we do not have velocity, so we don't have kinetic energy. But by the time the spring has launched the block away, it definitely does have kinetic energy. Then it reaches the rough patch, and the rough patch is stealing some of its energy. So its energy is going to go down. Then, up until T3, it's going to have constant energy, kinetic energy, because nothing's taking it. But as soon as it collides, because we know it's perfectly inelastic, that is an energy-stealing collision. So its energy is going to drop. Now we got to play, how do I connect them? Is it straight the whole way? Is it curved? Let's see. So this is what I thought was the trickiest part of the whole three free response is this graph right here. Figuring out how to connect them. So the dots I don't think were particularly difficult, but the connection is. So let's figure out the first part. So we know that A is equal to dv dt. And for a spring, F is equal to minus kx, which is A. Why did I do that? Well, this means that the force is going to be greatest at x0. So acceleration is actually the highest at the start, which is going to be the slope of the v graph. So our slope should be the highest at the start, meaning the slope should decrease. So we're going to get a concave down curve. Because again, it should make sense, because once you've reached compression, your velocity sort of is maxed out. So it shouldn't be increasing at an increasing rate. It should kind of be flattening out. Because again, if there's no friction here, then you'd flatten there for a while. So it should make sense that it's going to be concave down. All right, now what about friction? So if we were just graphing v as a function of t, it would be a straight line. But we're graphing v squared. So we're basically saying, what's the rate at which we're sort of losing kinetic energy? And it should make sense that if you are going the fastest at x1, then you're losing energy at the quickest rate at x1. So this means that we have a concave down curve. And maybe it shouldn't totally flatten out. Maybe I don't need to make it that severe, but I definitely want to make it concave down. And then finally from T2 to T3, well, there's no friction anymore, so this is constant. But then we sort of have a jump discontinuity at the collision time. So this is like a jump discontinuity, because right when this collision happens, boom, kinetic energy is lost to the environment in the collision. So we got, just to reiterate, we got concave down, constant, and a jump discontinuity. Now I'm sure they're pretty lenient with this. I'm sure they would even allow some variation of a continuous curve. I'd be curious how they actually grade this. But I thought this graph was really challenging. I have no idea how many points it's going to be. Much easier question, though. Using the principles of work and energy, justify why the graph shape of the first interval is the way it is. So, it says work and energy. So, the spring is doing work on the block. So, it's transferring energy to the block. And since it's transferring a positive amount of energy to the block as it slides, the kinetic energy change must be positive, thus the graph increases. So we'll pop over to my typed out version. The spring is external to the block and does positive work on the block. Since the net work on the block is equal to the change in its kinetic energy, I imagine that's the key here, citing that work equals delta Ke, K must increase. That is why the graph of K increases with time. I'm sure you had to explicitly say, since K increases, that is shown by my graph going up. So I don't think it's a shape thing. I think it's the fact that you must say K goes up because work is positive. So delta K is positive, as shown by my graph getting higher. So if I were to do this in a less formal way, I would say the net work is positive, which means that delta K is positive, which means that the graph rises from T0 to T1. And you'd almost think we had to do the ballistic pendulum thing here, but it's actually an oscillation question. So it says that when we attach our mass to this thing from a string of length L, we have some frequency F. What happens if our length instead was 2L? So the only thing that changes is doubling the length. And again, with these conceptual questions, it's often not just go with your gut instinct. There's probably a formula that relates these things. So the only thing that changes is L. And well, this is definitely a simple pendulum. Again, it's simple because this is not a rod. This is not a rod with thickness. It's a string. So from your lovely equation sheet, you can see that frequency is equal to 1 divided by 2 pi times square root of G divided by L. Or the one that most of you probably know better is the period of a simple pendulum. And this one you can get just by thinking about it. Because again, the period of a pendulum, it makes sense that it's longer with longer L's. So the frequency is the opposite because T is 1 over F. So here's what I would say. So I'd start with this frequency formula. We can assume that's a known fact. So since frequency is proportional to 1 over square root of L, as L increases, frequency decreases. It's repeating less often. So there's your that's as rock solid as you can get. It's a mathematical relationship. I'm dividing by a bigger number. Of course the frequency is going to go down. So the 2L frequency is higher for that reason. Some variation of that. Again, this is not the exclusive solution to this, but yeah. That was a neat little problem. I definitely thought this graph was really hard, but everything else I thought was nice. So I'm expecting a pretty high average score on this one. I do not share the same confidence for the other two in this set, which we'll explore next.